Well, there's 4 levels of protein structure. There's primary structure, which is the sequence of amino acids. For example, glutamic acid, leucine, valine, isoleucine, serine. The 1-letter abbreviations for those amino acids are E, L, V, I, S, and so that makes Elvis. Just a little joke, not very funny there. Secondary structure then is how that sequence is folded. Luckily for us, there's 2 examples of secondary structure, so that helps us to remember that this is secondary. The 2 examples of secondary structure are a helical structure called an alpha helix, or a sheet-like structure, kind of an undulating sheet, which is called a beta-pleated sheet. Tertiary structure is the 3-dimensional arrangement of how these helices and sheets are put together. And quaternary or quaternary structure, 4th-order structure, is how we put those three-dimensional structures into a whole protein, especially if we have repeating 3-dimensional structures. So we'll have 2 or 3 or 4 or more similar kinds of protein structures, which are all put together into one big superstructure. And when we do that, an example of that is quaternary structure. So here are the 4 levels of structure that we need to learn, each with their own objective. So this is the same thing as was on the previous slide, but just looking at it in a slightly different way. Primary structure, the order of amino acids in a protein. Secondary structure, either an alpha helix or a beta-pleated sheet. Tertiary structure, which is how we put those secondary structures together into a 3-dimensional arrangement. And then quaternary structure, in this example we're looking at a hemoglobin molecule. A hemoglobin molecule is made up of 2 alpha globins and 2 beta globins. And so when we put together those 2 alpha globins and those 2 beta globins, so a total of 4 separate protein chains folded in their characteristic arrangement, when we put those together into one big functional protein, then we call that quaternary structure. So primary structure is the order in which amino acids are strung together. Again, we're using the example of glutamic acid. The single letter abbreviation for that is E. Leucine, the single letter abbreviation is L. Valine, the single letter abbreviation is V. Isoleucine with an abbreviation of I. And serine with an abbreviation of S. So it turns out that there's actually a paper published where a bunch of investigators went looking for Elvis, who at the time was missing, and they found Elvis in the protein structure database, ELVIS. We'll take a look at those databases now.
In this short tutorial, I want to show you how we use these primary sequences to search in protein databases. The database that I'm using is from the National Center for Biotechnology Information, or NCBI, which is a division of the National Library of Medicine, NLM, which is a division of the National Institutes of Health, which is part of the government. And that explains the URL that you see at the top of the screen here in the menu bar. I'm going to do a search for a protein sequence. What I'm going to do is I'm going to search on my own name because I've deposited proteins sequences in the database, and the sequence that I deposited was one for actin in an animal called a ferret, Mustela putoris furo. And if I do Hutchins actin, I see that I have beta actin in Mustela putoris furo. And if I look down here, I can scroll down and see that the protein sequence is given to me. And so the first 10 letters of the protein sequence are HEK, RGI, LT, LK. And remember that those are the one-letter abbreviations that we didn't need to learn, but that we can use in the database. So this would start with histidine, and then the next would be glutamic acid, and then lysine, and so forth. Now we can take that sequence that I've just read off, and we can go backwards with that using something called BLAST. So if I go back to the page that I started with, I have BLAST here. And if I blast that sequence, what I'm doing is I'm searching for parts of the database that have that sequence. And so I'm going to do a protein blast, and then I'll enter the sequence, which I've saved before. And in just a few moments, and I may edit this out if it takes a while, it depends on how busy the servers at the government are at the particular moment in time that you do this, but in a few moments you should get a result back up. And this took about 30 seconds in real time, but I've edited that out, and what we see is a bunch of sequences that are homologous to the sequence that I've input. The top match is of course a perfect match, as we see here, to the same sequence that I started with. If we scroll down, then I'll notice all the possible matches, and not surprisingly I get a lot of other actins in other species as well.